Okay, now we will go directly to discuss something related to the confidence interval for the differences of two population means. And if you return back to the previous lecture, you can understand that we were dealing with just only one population, and at that time we used Z or T table by using the formula that has been used in the previous examples, and it is well known, and you do need to understand that we are dealing with certain area below the curve, dealing with the 95% or 1999 or 90%. So this is it was a general formula just only to estimate the confidence interval for certain just only one population to understand or to look for the average of something drawn from a large population. So from each of the two, so in this chapter we will deal with two populations. So we have two populations. From each of two population, an independent random sample is drawn. So we have two population, and we do need to draw two samples from those two population. The first sample mean we can call it or abbreviate it as x1 bar, and the second population is x2 bar. And we can calculate that actually from the drawn sample from the large population. So we have known x1 bar and x2 bar. So the mean for those two population, or the samples drawn from those two population, are known. So the difference is x1 bar minus x bar 2. So if we want to subtract the differences between the two samples, means actually from the two population, we can simply subtract them x1 bar minus x2 bar, which is an unbiased estimate of the differences between the two population means. And I will recall again, if we are dealing with large populations, you do need to know that their mu1 and mu2 are unknown. So our aim here, the objective of this thing, just only to know the differences between the two differences, or the confidence interval for the differences between the population means. So x1 bar and x2 bar are calculated for small sample that is drawn from large populations from the two large population. So mu1 and mu2 are the differences between the real mean for the first and the second population are unknown. The variances of the estimator is, if you want to just only to know the variance of the estimator, we can simply write them as sigma 1 square over n1 plus sigma square 2 over n2. This is the variance of the estimator. So you know that if you have sigma 1 square and sigma 2 square, it is the standard error. Now we have certain conditions for use in such examples or problems. Actually, we do need to assume that the population are normally distributed. There are three situations where we would determine the 100 by 1 minus alpha percent confidence interval for mu1 and mu2. And I will recall again, 100 times 1 minus alpha, we are dealing with the alpha, whether it is 5% or 1% or 10%. So the difference between them, we are dealing with this thing. And the main situation, we do need to assume that those two populations are normally distributed. This is the main assumption. If they are not normal distributed, we will go directly to certain things actually. So where the population variances are known, we do need to know that if the population variances are known, we will use Z. Where the population variances are unknown but equal, we can use T distribution or T tables or Z tables. Where the population variances are unknown but unequal, we do need to use T tables or T distribution. So you can return back to the flow chart that has been discussed previously, just whether to use Z or the conditions for using Z or T distribution. But in general, we do need to concentrate in on the variances, whether they are known or unknown. If they are known, we do need to use Z. If they are unknown, just directly go to the t-distribution. If the population variances are known, in this case, when the population variances are known, the alpha 1 minus alpha percent confidence interval for mu1 minus mu2 is given by this formula, and you can see x1 bar minus x2 bar plus minus the Z. Why do we use Z here? Because it is we are dealing with a population with known variance. So Z times 1 minus alpha over 2 will be used here. Now we do need to multiply it by the summation or the square root of the two variances. We are dealing now. We do need to understand if we do need to differentiate between this formula and the previous formula. The formula, the first formula or the previous lecture, we discussed just only one mean and one standard deviation, standard error actually. But now here we have two populations with two different means, okay, and two different variances actually. But we will use the reliability estimate here, which is Z over Z1 minus alpha over 2, is the same as we used previously. But the differences, as you see here, we do need to understand that we are dealing with two populations. We do need to understand also with that we are looking for the differences between those two population, and certainly you got it that we are dealing with two different variances. So here we add the square root of the sigma 1 square over n1 and plus sigma square 2 over n2. So we have sigma square 1, it is known, whether it is known or unknown. If it is known, as we indicated in the first in the above of this slide, we do need to add them here and divide them by the number of samples that have been drawn or has been drawn from the two populations. So n1 and n2 are the number of observations used for determining the variance, and just only it will give us the pooled. Actually, we will discuss the pool sample. Actually, it is the summation, square root of the summation of the standard deviation for both populations times or multiplied by the reliability estimate or the Z value or T value, whether if it is unknown variances. Now we have an example here. A researcher team is interested in difference between serum uric acid level in patients with and without Down syndrome. So we have two populations. One, the first one with Down syndrome, and the other one is without Down syndrome. The interested trait is serum uric acid level in certain patient. In large hospital for treatment of mentally retarded, a sample of 12 individuals with Down syndrome yielded a mean of x1 bar, which is 4.5. So we have the first known thing is the mean for the group of Down syndrome, which is 4.5. Okay. In general hospital, another hospital, a sample of 15. So we have the first N1 is 12 with a mean of 4.5. The second one with non-Down syndrome is 15 samples, normal individual. They are without, they are not of Down syndrome, and they are 15 normal patients. They are not patients actually, of the same age and sex, were found to have a mean value of x2 bar. Now we have the second mean, which is 3.4, and the n2 is 15. Okay, they are of the same age and the same sex actually. If it is reasonable to assume that the two population of values are normally distributed, now this is the first assumption, to assume that this population is normally distributed, as we previously mentioned, with variances equal to 1 and 1.5. So we have known variances. In this case, we do need to use what? The Z table, the Z distribution. Find, now we are determined, we do need to determine, to find the 95% confidence interval for mu1 minus mu2. Now from this case, you do need to understand that we are dealing with two populations, okay, with known we have two means. We have two samples known, sample size known, and two known variances. In this case, we do need to think about it, whether known or unknown variances. In this case, the known variances we use what we call Z distribution or Z tables directly. So this is how can we think about this equation before commencing in solving this example. Now we do need to summarize what we have, what kind of values that we have in this example. We have in the number of observation for the first population, which is 12. The mean, the first population is 4.5, and the sigma square 1, which is the variance for the first population, is 1. And also we have 15 samples for the second population with x bar of 3.5 and the variance is 1.5. Okay, so this is the things that to be think about, just to let you take it from the example, those values. Now again, we do need to return back to the previous lecture, and you do need to understand that we are dealing with alpha or 1 minus alpha. If we are dealing with alpha, it means that if we are dealing with 90%, it means it is 10%. If it is alpha, if we are dealing 1 minus alpha, 95%, in our case here in the example, we are concentrating in the 95%. He asked us actually to determine the confidence interval for 95%. Okay, so we have 95%, which is 0.05, 1.96, and also if we are dealing with 99% from the table, we draw it actually from the Z table or T table actually, 0.05, which is 2. The Z values here, as you see, it is Z value, Z table. If we are dealing with 0.9, it means we will use the reliability estimator in the equation. Okay, Z 1 minus alpha over 2, which is 1.645, just only to put this number if we are dealing with 9%. Now if we are dealing with 95%, it is 1.96. It's a fixed number. You can use it in all equations actually using Z table. And if we are dealing with 99%, we will use 2.575 as a Z value. Now we will solve this problem. Now we do need to understand the point estimate for M1 and M2 minus M2, the differences between the true population mean, the differences between them means is x1 bar minus x bar 2, because we draw small sample from this large population, so we'll subtract the two means from each other. So 4.5, which is the first population mean, minus 3.4 for the second population, that yielded 1.1. This is the differences between the two samples. Now we'll go directly to find the standard errors for those two populations. So we have sigma 1 square and sigma 2 square, and we know the number of observations that's drawn from those two samples. The first population mean, or sigma square 1, is 1. It is given in the it has been given in the example. So we are 1 over 12, with 12 is the N1, and 1.5 over 15 is the 15 is the second population observations, number of observations for the second population, and also the sigma square 2 is 1.5. It's known actually, given in the example. Just apply this equation, taking the square root of those additions, it will yield 0.4282. Now finally, you do need to understand that the main equation is x1 minus x bar plus minus alpha z 1 minus alpha over 2 by using 95% times the square root of the sigma square 1 over n1 plus sigma square 2 over n2. Sigma square, the standard error are known from the previous step. It is 0.4282, and 1.1 is the differences between x1 and minus x2 bars. Okay, that has been also calculated to be 1.1, and now 1.6 here, which is 1.6 times the standard error. From where we get it? We get it from the Z tables, which is 1.96. We are dealing with 95%. Okay, and from the previous slide, we can use it directly. Okay, you don't need to return back to the table. You do need to memorize them actually. Now this formula yielded what we call the confidence interval between the differences between the two means. If we add 1.5 to the right hand component results, which is 1.96 times 0.4282, it will yield, if we add it, it will be 1.94. If we subtract it, it will yield 0.26. So we have the interval, the confidence interval between the differences between the two means will be between 0.26 up to 1.94%. So we are confident now. How can we interpret our results? We are confident that the differences between we are confident by 95% that the differences between the two means is located between 0.26 up to 1.94. This is the general discussion. Now, if we have unknown, but they are equal, as we previously mentioned, we can use t values. It can be assumed that the population variances are equal. Then each sample variance is actually a point estimate of the same quantity. Therefore, we can combine the sample variances to form a pooled estimate. You do need to understand this slide. If we are dealing with unknown but equal variances in certain populations, it can be assumed that the population variances are equal. This is the first assumption. Then each sample variance is actually a point estimate of the same quantity. This is the second. So therefore, we will combine them to obtain the pooled estimate for those two unknown variances or the two populations. We will have what we call weight average or the pooled estimate. The pooled estimate of the common variance is made using weighted average. Okay, this is a procedure. The pooled estimate for the common variances, we will calculate it actually. We call it weighted average. This means that each sample variance is weighted by its degree of freedom. This is what do we mean by the weighted average? Just only the variances weighted by its degrees of freedom. This is the main idea between the weighted average or the pooled estimate of the common variances or variance. The pooled estimate of variances, as you see here, comes from the formula. We can calculate it from this formula. It's abbreviated as S square P. Okay. So S square P is the pooled estimate of the variance. The pooled. So we have two unknown variances. The general formula is N1 minus 1 times S1 square plus N2 minus 1 times S2 square over N1 plus N2 minus 2. This is the general formula for estimating the pooled estimate of the variances. So from this equation, N1 and N2 are the number of observation pair used in the two populations, and S12 and S2 square are the variances of the two populations. And as you see, the denominator is the same as the number of observations. The addition of the two samples or the two population samples minus 2. So this is the general formula, and it will be used for estimating the pooled estimate of the variance. Standard error of the estimate, as we see here, is abbreviated as S x1 bar dot x2 bar. S is the standard error. We will take just only the square root of the variances from the previous equation, and it will yield this thing. Okay, S1 bar, S1 x bar, S x1 bar dot x2 bar. It will yield the square root of the SP square over N1 plus S2 square, S2P square, S square P over N2. The S square P is calculated from the previous example, and you can just only add it to this formula just to obtain the standard error of the estimate that is necessary for obtaining the differences between the two population means. Confidence interval in this case, as you see from this formula, we will use the standard error which has been discussed, S2 bar S square P over N1 plus S square P over N2, and we will use the differences. This is the same formula that used previously, the differences between the two means, x1 bar minus x2 bar plus minus t. Now we'll use t, not z values or z tables, which is it will be, we will use, because it is unknown variances, we will go directly to use t values times or multiplied by the standard error of the differences between the two means, or we will take here the pooled estimate of the variances, s square p over the number of observations. Now we have an example. If we have two populations, we draw samples from those two populations for certain trait. We draw 13 samples from the first population. We calculate the mean for it to be 21, and we calculate also the standard, or the standard deviation for it to be 4.9. Into the second population number is 17, with 12.1 as a mean for those 17 samples. S2 is 5.6, and alpha here we want to use the 95% as a confidence interval. Okay, 95% means alpha is 0.05. Return back to the 2 or 3 slides from this equation, and also you can go back to the previous lecture to understand 0.05, from where we get it, and how can we assume it is 0.5 or 95% alpha or 1 minus alpha. Okay, now the calculations. The point estimate for M1 and M2 is x bar 1 minus x bar 2. Okay, so we have the two means, 21 minus 12.1, it will yield 8.5 or 9, sorry. And just only go directly to estimate the pooled estimate for the variances. We will use the previous example, the previous equation, which is S2, the pooled estimate, S square P equal to N1 minus 1 times the first variance plus N2 minus 1 times the second variance over the differences, or from the addition of the two samples numbers. Just applying the equation, the first N1 is 13, S1 is 4.9. As you see in the example, I gave you what? I gave you standard deviation, not the variance. The standard deviation from the previous, we understand and we know that the standard deviation is the square root of what? Of the variance. Return back to the previous lectures that has been discussed in the videos or in the classroom. Return back. We have a standard deviation. I gave you just only standard deviation. Now here in the equation we do need to use the variance. Just give it the standard deviation is the square root of the standard deviation. If we have the square root of the variance, we do need to double it actually. So we add 4.9 to the power of 2. Why? Just only to obtain the variance. If we have the variance, we will use it as it is, without any manipulation. So the second also 4.6, it is of 17 samples minus 1 times the standard deviation to the power of 2, and finally it will yield 28.21 just only by using simple calculations for obtaining the pooled estimate of the variance. Okay, so we have a 28.21. Put it in your mind. Tamam? Okay. The standard error here, we directly go to obtain the standard errors. We have the pooled estimate of the variance. Okay, S square P, we obtain it from the previous example. Just only add it in the equations for the standard error, which is the square root of the S square P over N1 plus S square 2 S square P over N2, and applying the equation, we have just only a pooled estimate of the variances, which is 28.21, that has been calculated from the previous equation, and divided by 13 and divided again over 17, take the square root, and it will be 1.9569. So we have the main values just only to use or to obtain the confidence interval. Now we'll go directly. The confidence interval, in this case we will use 8.9, which is x1 bar minus x bar 2 plus minus the reliability estimate for the t value, okay, in 95% or 95% or alpha 5% times the standard error. Standard error is obtained in the previous using the previous slide. You can go back just only to understand 1.9569 from where we get it. It's standard error, and times where it is the t-value. The t-value from the t-table, we can get it from there by using 95% and for those things, and it will yield this interval 4.9 and 12.9. It means that the differences between we are 95% confidence that the differences between the two means is located between 4.9 and 12.9. This is the differences between two means. Now the third case, in the population variances are unknown and not equal. As we previously mentioned, we do need to use also t-values, which unequal variances, the quantity used to calculate the test statistics does not follow the t-distribution. A substitution reliability factor called t prime has been proposed in this case. T prime, okay.